Hello, my name is Joshua Stein, and today I'll be discussing the advances and improvements in Hall effect thruster performance. This presentation will cover 5 papers that discuss improvements made to current Hall thruster technology. The first paper we will discuss is Numerical Optimization of Hall effect thrusters with Variation in Magnetic Field from the Department of Aerospace Engineering at the University of Petroleum and Energy Studies in India. The second paper we will look at is titled Performance and Thermal Characterization of the NASA 300 ms 20 kilowatt Hall effect thruster from JPL in Pasadena, California. Then we will cover magnetically shielded miniature Hall thrusters, design improvement, and performance analysis from UCLA and JPL in California. Next is Hall thruster modifications for reduced power operation from the Propulsion Physics Laboratory in Yavne, Israel. And finally, we will look at performance of double-channel tall-type thrusters from the Tokyo Metropolitan University in Tokyo, Japan. As a bit of recap from class, Hall effect thrusters, sometimes called HETs or HTs, are a form of electric propulsion that improves on the technology of the gridded ion engine. They offer better thrust density, require less power supplies, and remove the issue of grid erosion. The only significant trade-off of HETs is the slightly lower ISP of around 1400 seconds. HETs HETs generate thrust by applying a radial magnet and an axial electric field inside a discharge channel to charged particles. A positively biased anode injects neutral propellant into the channel and establishes the electric field, while a downstream cathode emits new electrons. The radial magnetic field traps electrons, forcing them into an azimuthal E cross B drift. The resulting ions are electrostatically accelerated out of the channel to generate thrust, and the electrons from the cathode neutralize the exhaust plume. This simple principle causes Hall effect thruster technology to be one of the most exciting electric propulsion technologies of our time. The first paper we will look at is Numerical Optimization of Hall effect thrusters with Variation in Magnetic Field. The overall premise for this paper is that experimental optimization of Hall thrusters is extremely expensive and slow. Each magnetic field change requires new hardware, vacuum testing, and long run times, which makes design iteration impractical. Instead, this paper focuses on numerical optimization, using physics-based plasma simulations to explore how changing the magnetic field configuration impacts thruster performance. They not only explore the field shape itself, but also how that field is generated. Specifically, they compare traditional electromagnetic coils, permanent magnets, and superconducting magnets, and measure their performance. For a conventional 5 kilowatt Hall thruster, the optimized magnetic field increased from the thrust from about 0.26 newtons to 0.69 newtons. With that, the specific impulse increased from roughly 1800 seconds to over 3000 seconds without increasing input power. The main takeaway from this paper is that magnetic field optimization alone, without changing propellant or scaling the thruster, can dramatically improve performance. The second paper, Performance and Thermal Characterization of the NASA 300 ms 20 kilowatt Hall effect thruster, shifts from numerical optimization to experimental validation. The key problem this paper addresses is wall erosion. In Hall thrusters, ions striking the discharge channel walls gradually erode the material, which ultimately limits thruster lifetime. The core contribution of this work is the experimental demonstration of magnetic shielding in high-power Hall thrusters, a form of shielding that works by shaping magnetic field lines near walls to limit erosion. They tested 2 magnetically shielded variants, the 300 ms and the 300 ms2, using physics-based Hall 2D plasma simulations to guide the design before testing. The testing performed showed that the thruster achieved peak total efficiencies of about 64% and specific impulse values up to 3050 seconds at 20 kilowatts and 700 volts. Performance nearly identical to the unshielded tests, but with the erosion reduced by over 3 orders of magnitude. The third paper builds directly on the previous one, but applies magnetic shielding to the more challenging case of miniature Hall thrusters. Hall thruster lifetime is limited by erosion, and because miniature Hall thrusters have much larger surface to volume ratios than that of traditional Hall thrusters, this problem becomes worse. This paper investigates whether magnetic shielding, which worked well at 20 kilowatts, is still viable at much smaller power levels. The authors experimentally compared an unshielded miniature Hall thruster to a magnetically shielded version called the MASMI-60. They measured thrust, anode-specific impulse, anode efficiency, and most importantly, plasma potential near the channel walls, which directly relates to erosion. The Hall 2D simulations showed that the configuration successfully pushed plasma potential away from the walls, which was confirmed experimentally by the existence of white erosion bands on the baseline, with no erosion bands on the shielded thruster. The takeaway here is that magnetic shielding remains effective even at miniature scales, reinforcing the results of paper 2 and showing that this approach scales down, not just up. The fourth paper shifts to a different but equally important challenge, operating Hall thrusters at very low power levels. At power levels about 300 watts, Hall thrusters tend to lose efficiency and suffer from stability issues. Traditionally, the approach has been to scale down the geometry of larger thrusters, but this tends to lead to a significant decrease in lifetime and performance. This paper takes the approach of modifying an existing 600-watt thruster so it can operate stably in the 200 to 300-watt range. The key change is reversing the magnetic field lines near the anode, along with increasing the length of the discharge channel. The idea is to slow electron axial drift near the anode, increase electron density in that region, and improve ionization efficiency at low power. The thruster demonstrated specific impulse values of about 1370 seconds and efficiencies near 32% at roughly 340 watts, meaning they achieved stable operation at the lower wattage they were aiming for. The takeaway is that HT performance at low power can be preserved better by reconfiguring existing thrusters rather than scaling them down. The final paper, Performance of Double-Channel Tall-Type Thruster, looks at improving Hall thruster performance through structural redesign rather than magnetic field shaping or operational changes, specifically by implementing a double-channel anode layer. The authors experimentally tested a double-channel thruster, the TMU DO58, in a vacuum chamber, comparing single channel and dual channel operation. In single channel mode, the inner channel achieved a maximum anode efficiency of about 43% at roughly 500 watts, while the outer channel reached 42% at around 900 watts. They also found that discharge channel geometry plays a critical role, finding that the optimal channel width of 6 mm produced the highest performance. Overall, this paper shows that multi-channel HETs can be an effective way to improve performance and power scalability, adding to the magnetic and operational optimization strategies discussed in the earlier papers. Together, these 5 papers show that Hall effect thruster technology has reached a very mature and capable state. Physics-based optimization techniques have allowed engineers to significantly improve performance without costly testing, and physical experimentation has backed these results. Magnetic shielding has emerged as one of the most important breakthroughs, giving us orders of magnitude better erosion reduction. At the same time, we've seen that stable and efficient operation of HETs can be achieved across a wide range of power levels through reconfiguration and redesign rather than geometric scaling. Looking forward, the next major advances will come through the combination of the techniques I've discussed, along with long-duration lifetime testing under mission-relevant conditions. Beyond that, system-level optimization for efficiency, mass, cost, and reliability are going to be what pushes Hall effect thruster advances to the next frontier. As our technologies mature, Hall effect thrusters will continue to be more and more valuable for high-power, deep space missions. Thanks for watching.